Hello everyone, welcome back to our Microservice Masterclass series. In last video, we learned that every microservice should own and control its data. We also learned that one service should never directly access another service database. This gives a better independence and clear data ownership, but it creates a new challenge. Suppose the user wants to see complete order detail including order information, current inventory status, payment status. This information is stored in three different databases. We cannot use a normal database join because the database being separated belongs to separate service. So how do we query this data? And how do we keep data synchronized across service? That is exactly what we will understand in this video. So let's begin with the first section. The cross service query problem. In a monolithic application, creating an order detail page is relatively simple. We can write one SQL query that join the order, inventory and payment tables. But in a microservices architecture, these tables may not exist in the same database. So the order service has its own database, inventory has its own database, and the payment service has its own database. The order service should not directly connect to the inventory or payment database. Doing that would break service ownership and create tight coupling. Therefore, direct database join across services should be avoided. Correct? Imagine that client requests the detail of order 101. The final response may need order ID, order status, inventory status, and payment status. No single query may have all this information. This is called the cross service query problem. There are two common ways to solve it. The first is to collect data in a collect data at request time using API composition. The second is to create a separate query ready copy using events, read models and materialized view. Let's understand the first approach, API composition. Look at the left side of the diagram. The client send one request to an API composer. The API the API composer then calls order service, inventory service and payment service. Each service reads its own database and return its part of information. And the API composer combines this response and return one final result to the client. The client does not need to understand how many internal services are involved. This is called API composition pattern, right? For example, the API composer may call like get call with orders 101, get call with inventory 101, get call with the payment 101, right? Then combines all three responsive into one order detailed response. API composition is simple and useful when a few services are involved. When few services are involved, the amount of data is limited. The client need current information and the dependent service responds quickly. But there are some challenges. If 5 services called sequentially, the total response time becomes sum of all 5 calls. To reduce the latency, independent call can be executed in parallel, but even the parallel calls, the final response usually depend on the slowest service. True. We must also decide what to do when one service is unavailable. For example, if payment service fails, should the complete request fails or should we return the available order and inventory information with the payment status marked as a temporarily unavailable? This decision depends on the business requirement completely. The API composition works well for simple queries, but it becomes expensive when many services or large data sets are involved. For those situations, the event-based synchronization can be a better solution. Now look at the right side of the diagram. The order inventory and the payment service publishes event whenever their data changes. Whenever their data changes. For example, the order service may publish order created, order confirmed, and order cancelled. The inventory service may publish inventory reserved, inventory released, and the payment service may publish payment completed or payment failed. These events these events are sent to an event broker. Another component consume the event and maintain a query ready copy of required data. Suppose the order service publishes order created. The query stores the query store create a new order record. Later the inventory service publishes inventory resolved. The same record is updated with the inventory status, and finally the payment service publish payment completed. The payment status is added. Now the complete order information is available in one place for reading. The original service is still on the data. The new store contain only the synchronized copy created for query. This approach reduces runtime calls between services and provide faster reads. However, event synchronization is asynchronous, therefore the copy may not be updated immediately. We will discuss this as a stale data in few minutes. Materialized view. A materialized view is pre-built representation of the data collected from multiple sources. A materialized view is a pre-built representation of data collected from multiple services. Instead of joining information every time a request arrives, we prepare a combined data in advance. For example, we create an order summary view containing order ID, customer name, order status, inventory, payment status, and total amount, right? When an order, inventory, or payment event arrives, the materialized view is updated. When the client requested the order summary, the application reads it and directly from this view. No call to order, inventory, or payment service is required at request time. This provides several benefits: faster queries, fewer network calls, reduced load on source services, better availability for read operations, easier reporting. A materialized view can be stored in a relational database, a document database, Redis, OpenSearch, a data warehouse. The technology should be selected according to the query requirement. Notice something important: the materialized view is not the source of truth. If the view is deleted, we should be able to rebuild it from source data and store event. The original microservice remain the owner of the business data. Next is read models. A read model is a data set specifically for the particular query or user interface. The sum database is usually designed according to the business operation, but that structure may not be ideal for every screen. For example, a customer order history page may require order date, product name, total amount, payment status, delivery status. An operations dashboard may require failed payment, delayed orders, unavailable inventory, orders pending for more than 10 minutes, Both views use order related information, but their data structure are different. Instead of forcing one general model for serve Instead of forcing one general model to serve every query, we can build separate read models. For example, customer order history model, operation dashboard model, daily sales model. Each model stores only the information required to that use case. This makes read faster and keep query logic simple. And this separation of write and read model is also an important idea behind CQRS, which we will study in the dedicated upcoming episode. Handling Next topic is handling stale data. Event based synchronization introduces eventual consistency. Suppose the payment service complete a payment at 10 o'clock. It publishes payment complete event. The read model receives and processes the event at 10 o'clock and 2 seconds on 10 o'clock 2 seconds. For those 2 seconds, the payment service says the payment is successful, but the read model may still show it as a pending. This is called stale data. Stale data is not always a system failure. It can be expected temporary state in a synchronous architecture. And the important question is, how much delay can the business accept? For an analytic dashboard, a delay of a minute may be acceptable. For an order status page, a few seconds may be acceptable, but for financial and security decision, the latest information may be required immediately. In those cases, we may verify the data directly with the owning service. The user's interface should also handle intermediate such states such as processing, pending confirmation, updating, payment verification in progress. We should monitor synchronization, delay, and define acceptable freshness limits for every read models. Next topic is replication and caching. Data replication and caching can reduce repeated service call and improve read performance. Suppose the order service frequently needs a product name and category. Calling the product service for every order request may create unnecessary latency. The order service can maintain a local copy of required product information and update it through the event. The important rule is replicate only the data required by service. Replicate only the data required by service. Do not copy the complete product database if only the product name and categories are needed. Caching is another option. Frequently requested data can be stored in Redis or in memory cache, but every cache introduces important question. When should the cache value expire? How will it be invalidated? What happens if the cache is unavailable? Can the application temporarily use an order value? For data that changes rarely, time-based expiration may be enough. For important update, event can be used to invalidate or refresh the cache. The database should generally remain the durable source while the cache improve the performance. The next topic is reporting and monitoring. Reporting across multiple services should not depend on running heavy queries directly against the production service database. Imagine a daily sales report that needs millions of orders, payments, and customers and product. Calling multiple production API is every report would be slow and could affect the application traffic. A better approach is to publish a required data to the reporting database, data warehouse, or an analytic platform. The reporting system maintains its own optimized data model, but synchronized data must be monitored carefully. Important metric includes event processing lag, failed synchronization event, DLQ, age of latest updated records, missing and duplicate events, source and read model event, consistency check failure. We should also maintain event ID, timestamp, and correlation ID. These identifiers help us track when a record changes, when the event was published, and when the read model processed it. For critical data, we can run periodic reconciliations jobs. These jobs compare the source of truth and with a synchronized copy and repair missing and incorrect data. Let's quickly recap the complete diagram. When services on separate database, we cannot directly join their tables. For simple and current queries, we can use API composition to call multiple services and combine their responses. For faster and more complex queries, services can publish event to synchronize data into the materialized view and read model. Read model shape the data for a specific screen and reporting requirement. Business event synchronization is asynchronous. We must design for temporary stale data. Replication and caching can improve performance, but they require clear ownership and refresh strategy. Finally, reporting system synchronized view must be monitored for freshness, failure, and consistency. The main lesson is keep business data ownership inside the service but create query specific copy when the application needs fast combined view. That completes our discussion of data management in microservice. In the next episode, we will begin another important topic, distributed transaction in microservice. If you found this video helpful, please like this video, subscribe to my YouTube channel, and share it with anyone learning microservice and system design. Thank you for watching. I'll see you in the next episode of Microservice Masterclass.